Good. Okay, my presentation is divided into 4 main parts. I would like to start with the introduction to perovskite solar cells. So perovskite solar cells is a novel photovoltaic technology based on hybrid lead halide perovskite. The perovskite solar cells during the last years caught the attention of the scientific community. It's a type of cell that includes perovskite structured compounds. The general formula of the crystal structure of the absorbable materials is ABX3, where AAB are cations with different sizes and X is an anion halide. Hybrid organic, inorganic perovskites are most commonly used materials as light harvesting active layer. The metallimoninium lead halide is the most common perovskite absorber. In the general structure of the perovskite solar cells, the perovskite material is sandwiched among selective transport layers, which are the electron transport layer and the hole transport layer. It absorbs the light and transport charges to the selective contacts, which are the ITO and the gold contacts. The research on this type of cell has been exponentially increasing over the last decades. Obviously, this cell provides us some advantages, which are the following. High efficiency up to 25.7%. We can see here there is a fast rise in efficiency since its appearance in 2009 with an efficiency of 3.8. Fast low temperature solution-based fabrication method. So we can do sintering at low temperature, below 100 degrees. High absorption coefficient. In a small thickness, they can absorb a large amount of light. Higher stability in air. Tunable band gap tuned in between 1.55 electron volt to 1.17 electron volt when we are switching between lead to tin for the B cation. And very low cost, material cost. So the fabrication of perovskite solar cells flexible have tremendous interest because it's combined sorry. So because it's combined low embodied energy below 100 degrees, low manufacturing cost, high efficiency exceeding 20%, then we can see that the efficiency is increasing year after year. The common used substrates are polyethylene terephthalate and polyethylene naphthalate, PET and PEN. They provide good transparency, good flexibility, lightweight. They are bendable, low cost of high optical transparency with low transmittance compared to glass ITO substrates. So flexible PV can be integrated onto surface curves such as roof tiles, round-shaped consumer products. Its application into wearable electronics such as PV integrated bags, hats, and shirts. As I said that in perovskite solar cells there is several layers. So our work is to focus on one layer, which is the electron transport layer. So why this layer is important? It improves the extraction rate of photo-generated electrons. It ensures the formation of selective electron contact with light-absorbing perovskite layer and prevents the hole migration to the counter electrodes and reduces charge recombination. For this purpose, the ETL should have well-matched advanced structure with the perovskite materials and have high electron mobility, high transmittance in the UV visible region, and good morphology to ensure the formation of high-quality perovskite film. The electron transport layer, it could be simple, single ETL such as tin oxide, titanium oxide, zinc oxide, etc., or composite ETL, double, like zinc oxide with the tin oxide or doped tin oxide. So we have made different studies on this layer. The first, we have fabricated different sets of perovskite soil cells, keeping the same film, perovskite film, the same whole transport layer, the same gold contacts, and the same substrate, which is the beta-ITO. And each time we change the electron transport layer, we have found different efficiency. At second time, we have fabricated another set of perovskite soil cells, keeping the same perovskite film, the same whole transport layer, the same electron transport layer, the same gold contacts. And for each same type of electron transport layer, we have changed the substrate. So moving from glass ITO to PET ITO. Each time we change the substrate, we have found a different efficiency. So here we have two main studies. The first one is to study the properties of a good electron transport layer for flexible perovskite soil cells, and to study the differences of electron transport layers fabricated on flexible PET compared to those fabricated on glass. So now let's move on to the experimental part, the fabrication of perovskite soil cells. Starting with the different solutions made for the fabrication of perovskite soil cells. For the perovskite solution and the spiral method, so which is the whole transport layer, they are the same recipes used for all sets of perovskite soil cells fabricated. For the ETLs, we have 12 ETLs based on 9 different kinds of solutions, which are tin oxide nanoparticles, tin oxide made from liquid precursor, zinc oxide, magnesium oxide, aluminum oxide, potassium hydroxide. We have 2 types of solid-state ionic liquid and mesoporous titanium oxide. Moving on to the steps of the fabrication of the cells. Starting with the deposition of the electron transport layer, and then we do the annealing. Of course, we have different electron transport layers, so we have different annealing temperature. Then we do the UV treatment to enhance the wetting properties of the ETL. Then we do the deposition of the perovskite film and anneal it at 100 for 1 hour. Then we do the deposition of the whole transport layer, which is the spiral or method. Then the device is completed with the deposition of the gold contacts. So now let's turn on to the first part of the results. With the first part is 12 electron transport layers based on tin oxide. So we have fabricated 12 different sets of perovskite soil cells on PET ITO substrates, each with a distant ETL based on tin oxide as the common material. There were 5 different architectures of flexible perovskite soil cells in 12 different material configurations in total. The first type consisted in perovskite soil cells with tin oxide layers. We have 2 different electron transport tin oxide were tested here. The first one is made from ready-made nanoparticles, and the second one is made from liquid precursor. The second type contained a bilayer of tin oxide with an ionic liquid. So as I said previously, that we have 2 ionic liquids here. The third type consisted in bilayers with a second metal oxide. Here they are the zinc oxide and magnesium oxide. They are deposited below the tin oxide ETL. In contrast, the fourth configuration, the metal oxide, which are the magnesium oxide, aluminum oxide, or the mesoporous titanium oxide, was deposited over the tin oxide layer. The last configuration, the tin oxide, were subjected to 3 types of interface treatment using the water and potassium hydroxide. As we can see in this graph, that each time cells with tin oxide ETLs were fabricated and used as reference devices, and the efficiency of the other configurations are normalized to the average efficiency of the reference cells to take into account the fluctuations in performance that can occur from batch to batch and over different periods of time. Here, we can see that the bilayer of zinc oxide tin oxide delivers the best efficiency, the best performance perovskite soil cells. And when switching from tin oxide nanoparticles to tin oxide liquid precursor, there is an enhancement in efficiency by 215%. So we are going to discuss only the batch that contain tin oxide nanoparticles with the zinc oxide tin oxide bilayer. In the first graph, JV curves of the cells and the elimination of tin oxide single layer and zinc oxide tin oxide bilayer and the Watson elimination. The efficiency improved by, on average, let's say, by 39%. And we can see that when moving from tin oxide single layer to zinc oxide tin oxide bilayer, there is suppressed hysteresis. For the dark JV curves of the same cells, we see that zinc oxide tin oxide based cell provides a dark current of 67.4 lower, but the on current is 75.5 higher for the zinc oxide single layer. For the stability measurements, we can see that the cell with tin oxide only is more stable. So for the zinc oxide tin oxide bilayer, the stability was about only 2 hours. So we can say that the tin bilayer based cell leads to suppressed hysteresis, better blocking behavior, and poor stability. The reason improved for fresh cells of the zinc oxide tin oxide bilayer and its poor stability. We can see the same images of the perovskite on the single layer tin oxide and the perovskite on the bilayer zinc oxide tin oxide. We can see that the grain size of the perovskite on the bilayer was found to be larger. Oxide on this contributes to an improvement in Few factor and the open circuit voltage, which explains the enhancement in efficiency of the fresh cells of the zinc oxide tin oxide bilayer, as well as the suppressed hysteresis behavior, confirming the previous results. Whereas for the same images of the ETLs, we have for the tin oxide only and zinc oxide tin oxide bilayer, we can see that the surface of the zinc oxide tin oxide was rougher than the tin oxide nanoparticle only, which can be attributed to the granular nanoparticles of the zinc oxide. For the EDX analysis, it reveals that the surface of the zinc oxide tin oxide, there is presence of the zinc. So confirming that the tin oxide overlay did not completely avoid direct interaction between the perovskite films and the zinc oxide in the layer, leading to the perovskite interaction because of the hydroxide groups of the zinc oxide on the surface of zinc oxide. So here it explains the poor stability of the zinc oxide tin oxide bilayer. Let's move on to the second part, which is the first main study of this work, properties of high performance ETLs for flexible devices. So here we have fabricated new sets of perovskite soil cells on flexible and glass substrates to first study the properties, then to study the differences between cells on PETs and glass devices, glass substrates, sorry. So here we have kept only 3 configurations, 4 ETLs in total. So as we can see here that the efficiency is affected by the type of the ETL. So every time we change the ETL on the PET, there is a new efficiency. So for this purpose, we have studied the dependence of the efficiency on the series and shunt resistance. We can see that for the shunt resistance, the efficiency doubles from 5 for the bilayer on tin oxide aluminum oxide to 9.5% for the zinc oxide tin oxide, when the shunt resistance increases by a factor of 3, which is attributed to a limited recombination loss. Whereas there is small variation of the series resistance compared to the shunt resistance, there is a decrease by a factor of 2, but also it is attributed to high electromobility, well-matched energy levels, and ensured improved interface and high quality perovskite film. Now let's move on to the third part. We have analyzed the PET cells versus glass cells devices, performance differences between flexible and rigid salt cells. So firstly, we have studied the dependence of the efficiency on series resistance, shunt resistance, on current, and the reverse current. We can see here that there is a decrease of about 10% for the series resistance for glass cells here, with an efficiency increasing by 29%. And for the shunt resistance, it doubles for the glass devices, with an efficiency also increasing by 29%. For the dark current or the fast current, it is lower by 76% on average for the glass devices, with the PCE increasing by 29%. The improvement in the shunt resistance provides or delivers 15.6% in short current density, and an improvement also of about 6.9% of the Phi factor. Also, the dark current, as it is low for the glass devices, it provides also an increase in the short current density and the Phi factor also. The improvement, so in order to ascertain the origin of the better quality of the electron transport on glass devices or substrates, the resulting better shunt resistance, series resistance, dark current, and efficiency, we have performed contact angle measurements, since it is the ATO, the electron transport layer, and the perovskite interface which determines to a great extent the series resistance, the better blocking behavior, and the cells. So we can see that the contact angle of the tin oxide layers increased from 49 for glass cells to 77 for PET samples. So the better wetting at the interface ensures the formation of a perovskite film free of pinholes that would form shunt paths by inducing direct contact between electron transport layer and the hot transport layer, and they reduce the open circuit voltage and the Phi factor. So we have a trend here that better wetting at the interfaces of glass samples leads to higher power conversion efficiency. So that brings me to the end of my presentation, and to conclude the first part, we have among all the 12 electron transport layers, the zinc oxide, tin oxide delivers the highest efficiency of 14.8%. And the zinc oxide made from nanoparticles is better than the tin oxide made from liquid precursor, and there is an improvement in efficiency of 215%. The tin oxide made from nanoparticles ETL is more stable than all double electrotransport layer. In the second part, the property of a good electrotransport layer for flexible devices, we should ensure there is an enhancement in the blocking behavior of the ETL. And in third part, the differences between PET cells and glass cells. There is a relation between the wetting property of the conductive substrate, the ETL system, so the interfaces between the ETL and the perovskite film, and the final performance. So I would like to thank Professor Thomas Brown from the University of Rome, Tor Vergata, and Professor Francesca Brunetti, Doctors Giulia Lucalelli, Francesca Di Rossi, Baba Akhtari for the contribution in this work. And I would like to thank all the funders. Thank you for your attention. And if you have any question, I would be happy to answer them.